SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of applied thermal engineering, and the topic of our today's discussion is the multi-fluid cycle and its analysis. So, if we try to recall, in this module of this course we have discussed about steam power cycles. Starting with the Carnot cycle, we have discussed several other cycles which are used in real applications. Importantly, in all these cycles we have seen that the working fluid is water or steam. So, we have identified that there are two parts in the cycle, one is the high temperature part, another is the low temperature part, and the working fluid which changes its phase from the low temperature part to the high temperature part. Now, in the last class we have discussed about the desirable properties of the working fluid which will be used in the steam power cycle, and we have seen, rather we have discussed, though water is predominantly used as the working fluid, but it is not considered as the ideal fluid. In fact, water has a few drawbacks, and if we need to consider water as the ideal working fluid, all these shortcomings need to be eliminated, and one way of doing, rather considering this aspect is the use of binary cycle or the combined fluid cycle. So, the necessity of the combined cycle arises from the fact that we would like to use water as the working substance or working fluid despite knowing its a few drawbacks, but our objective should be to eliminate all these drawbacks, and in doing so we need to consider the multi-fluid cycle or the binary cycle. So, now if we try to write down the desirable properties of the working fluid. Number one is just I am writing high critical temperature at a reasonably low pressure. Number 2 is low triple point temperature, that is the freezing temperature should be below the room temperature, low triple point temperature and then high enthalpy of vaporization or high heat of vaporization. Okay. And finally, it should not have low condensation pressure, rather vapor pressure should be relatively closer to the nearly closer to the atmospheric at a desirable condensation temperature. So, I am writing this is high heat of vaporization. The meaning of this particular is, what is the meaning of this? We should look at this particular property. If we can ensure, then mass or weight of the fluid in the cycle will be minimum. So, low condenser pressure is not allowed. Is not allowed. In addition to this, we had discussed that it should be non-corrosive, chemically stable, easily available, and also what I am telling, non-toxic. Okay. One most important, in addition to these properties, most important which should be discussed today is that it should have ability to wet the surface of the metal. So, metal surface. To increase heat transfer. Now, why I am discussing this part again today? High critical temperature at a reasonably low pressure, it is very important. It is very difficult to have all these properties in water. You know that if we try to recall that in steam, when we are getting steam in the boiler, rise in temperature of steam is accompanied with the rise in pressure. So, we have seen that at a critical temperature, if we consider steam, so pressure is very high. So, if I focus on this particular point, then we can write that. So, this is very important, that means we should look for the working fluid which will be having high critical temperature at a reasonably low pressure. So, that means we can increase the temperature without increasing the pressure. As I told you, for steam, rise in temperature is accompanied with a rise in pressure. For at a critical temperature, so I am writing for steam critical temperature steam water mixture, if we use as the working fluid, critical temperature 374 degree Celsius, pressure is 225 bar. So, try to understand, if we use water as the working fluid and when that water is getting converted into steam in the boiler, even at the critical temperature pressure is very high. So, if pressure is very high, then we also need to look at 3 different issues. One is design, operation and control. So, to withstand that high pressure, design of the device in which this conversion or steam will be generated, its operation as well as control will be an issue. So, these 3 important issues like design, operation and control are the factors for which we should look for a fluid which will be having high critical temperature at a reasonably low pressure, right. Low triple point temperature, I mean what is the, why you need to have high critical temperature, because if we increase high critical temperature, that means the maximum temperature at which heat would be transferred, I mean when it would be very high, and the maximum temperature at which heat will be transferred from the from the combustion will be getting energy, that energy should be transferred to the working fluid. And now, if the critical temperature is very high, then it is highly possible to have phase change when working fluid will be changing its phase. That process can be maintained even at a high temperature. So, we shall be trying to mimic or closer to the Carnot cycle. Low triple point temperature. So, basically I have mentioned, if that is the case, then freezing temperature, I mean freezing temperature should be well below the atmospheric temperature. So, that is what is ensured, and high heat of vaporization I have already told that it ensure that it will ensure that the working weight of the working fluid should be minimum, and finally low condenser pressure is not allowed, that we have discussed in the previous class. So, question is, if we use water as the working fluid, it is very unlikely to have all these properties at a time, and that is how, despite the fact that we will not be getting all these properties in water, we need to use water, because it is used predominantly because of its a few advantageous feature, but if you would like to use it essentially to increase the efficiency of the plant, we need to go for the binary cycle. So, the concept of binary cycle is coming from this particular fact. Now, let us look into this aspect. If we consider this is boiler, this is turbine, this is pump, so this is 1, 2, 3, 4 turbine, this is condenser. So, this is Q out, W out, this is Q in, this is W in. So, try to understand that so essentially we can write this. So, this cycle is, this is a, I mean all the processes are executed in a cyclic manner, and if we can consider the equivalent form of these cyclic processes like this. So, this is QH, that is TH, TL, QL and W net. That is what we have learned in our basic thermodynamics course. So, you know that if we try to understand that W out minus W in, that is the net work that we are getting from the cyclic process. So, if what I am trying, I am trying to represent the all these processes through this heat engine. So, essentially this is the engine which is operating between two temperature thermal reservoirs, one is at high temperature, another is at low temperature, and we are getting continuous work output. So, essentially this is the representation, or a very simplest form of this system. So, what we know from the efficiency, that thermal efficiency of this TL and this is TH. So, this is the thermal efficiency of this cycle, which we can, if we look at this heat engine, we can see that efficiency will increase, it will be TL minus TH. So, W net by Q in, so we are writing W net by Q in, so that is QH. So, that is what we can write is QH minus QL divided by QH 1 minus QL by QH, right. So, W net plus QL is equal to QH. So, W net is equal to QH minus QL. So, we can write this for the reversible cycle, and what we can see that if we increase the temperature, this fellow, so if we try to write it using this color, so if we try to increase this fellow, so that means temperature at which heat is added should be maximum. Also, this temperature of sink to which heat is rejected, this also should be minimum. So, either by reducing TL or by increasing TH, we can ensure that the efficiency of the cycle will be maximum. Now, question is, if we go back to the previous slide, rather if we just look at the simple form of this steam power cycle and its equivalent representation that is shown over here, our objective should be the amount, the TH should be maximum. So, the maximum temperature, I mean the temperature at which heat is added to the working fluid should be maximum. That means, and the temperature at which heat is rejected, that also should be minimum. This is not always possible to reduce temperature, because it is dictated by the temperature of the coolant which is available near the plant. So, what we can do, we can try our best to keep this TH as maximum as possible, and if you would like to do it, if you would like to do so, then what I wrote over here is that high critical temperature at a reasonably low pressure. So, that means the working fluid should be chosen in such a way that the critical temperature should be very high, so that we can increase the maximum temperature at which the substance will change its phase will be high, so that the latent heat transfer or phase change heat transfer will be it is more efficient. So, I mean we can achieve high thermal efficiency. Problem with water is that, as I told you, a rise in temperature is accompanied with a rise in pressure, and that eventually creates problem from the perspective of the design, operation as well as control of the plant. So, that is why water alone cannot be used as the working fluid if we need to have or achieve high thermal efficiency, and it is because of this reason the concept of binary or the combined fluid cycle is there. Okay. So, if I go to the combined fluid or binary vapor cycle, combined fluid or binary fluid cycle. Okay. So, you know that different working fluids are having different attractive features, but not all of, I mean if we consider water and other oil. So, all these fluids are having different attractive feature in them, but not all. So, the properties or attractive feature water is having, those features are absent in oil. In a similar way, the attractive features oil is having, maybe those features are absent when we look at water as the working fluid. So, this is very important, and in such a case two vapor cycles operating on two fluids are put together. So, two vapor cycles operating on two working fluid are put together, right. One is at high temperature and another is at low temperature. So, that means our objective is to get the attractive features of two different fluids, rather our aim should be to achieve or to attain attractive features of two different working fluids, and if you would like to get those, we need to consider two vapor cycles, each of them will be operating on each working fluid, and if we combine them together, one will be at a high temperature, one or another is at a low temperature, and this total arrangement is known as the combined fluid cycle. Question is, water will be used as one working fluid, definitely for the low temperature part of the cycle. I mean there are two different cycles. Water will be used as the working fluid for the low temperature cycle, while we also need to select another fluid which will be used as the working fluid for the high temperature part of the cycle. Now, next question is which fluid should be selected to act as the working fluid for the high temperature part of the cycle. In this context, it is seen that mercury is used as the working fluid for the high temperature part of the cycle or high temperature cycle, not part, high temperature cycle. See, I mean, although mercury does not have all the desirable properties which we have talked about in the beginning of today's class, yet mercury it is used because of it a few distinctive features, we shall discuss all those. So, the combined cycle that we are going to discuss today is known as mercury water combined cycle. So, if we go to the next slide, so we shall be discussing about mercury water combined vapor cycles. Okay. So, let us draw the schematic depiction that will help us to understand very quickly. If I draw it, there are two different part. One is, this is the so this is HG cycle and this is high temperature part, and so this is, you know, it is connected to electric generator. So, this is electric generator. So, this is turbine. Okay. So, this is mercury generator. So, this is mercury generator. So, you can understand we need to supply heat in this mercury. Another part of the cycle that I am going to draw now is the, so basically, you know, this is combined fluid cycle. Till now we have drawn only the mercury cycle. So, remaining another low temperature cycle is the water cycle, water or steam water cycle. So, if we write, so say we are supplying water and that water is getting converted into steam, and that steam will be collected, will be allowed to pass through the superheater, and that will be taken to another turbine. From there we will be getting W out. So, this is turbine, right, and after doing work that steam will be collected in a condenser. This is as usual. So, here heat will be rejected and the collected condensate will be pumped back to the, you know, this is called steam generator. So, this is steam generator and this is pump 2. So, you can understand, and this is water cycle or steam cycle. This is steam turbine, and if I write, this is Mercury turbine. Okay. So, this is also that we are calling it. So, it is very easy to understand. There are two different cycles, two different fluids are used. Objective is to increase the efficiency of this cycle. What is done? Heat is supplied to this mercury, because mercury is having high critical temperature at a reasonably low pressure. Mercury is having high critical temperature at a reasonably low pressure. So, we can increase the critical temperature, and the isothermal heat transfer from this external source to mercury is very high, and what will happen, that mercury vapor will be allowed to go through the mercury turbine. It will, this turbine is connected to this generator. Now, after doing some work, that mercury should be again collected in this device, which we have given name as the steam generator. I also can call it mercury condenser. That means, here mercury is allowed to reduce its temperature by supplying water, and that water will be converted into steam. That steam is taken through superheater. So, this is superheated. This is superheated. We shall discuss, this is for the timing, you keep in mind that this is again a device through which steam is allowed to pass, essentially to increase its temperature before it enters into the boiler, into the turbine. So, you know that whatever steam is generated in this steam generator is in contact with the water. So, essentially the steam that we are getting is saturated steam. So, to increase the quality of the steam, rather we need to superheat, and that is why it is passed through superheater. This is what I have schematically shown. We shall discuss this part again when we shall be discussing about boiler, and that superheated steam is taken to the steam turbine and it does work, and we are getting W out, and after doing work steam is collected in condenser, wherein it rejects heat Q out, and that condensate is pumped back to the steam generator. In this way you can understand. So, this is also a cyclic process, and the process that is there in this cycle is also cyclic. All the processes are cyclic, I mean executed in this cyclic manner. Idea is what we can get out of it. So, you know that again if we try to represent the entire system, equivalent form should be like this. So, equivalent representation of this complex circuit is this. What we can understand, we are supplying heat from a heat source which is now having temperature Th, and eventually heat is rejected in another reservoir, that is heat sink, which is having temperature TL, and it is out of this heat transfer to the device, and from where heat is rejected we are getting W net. So, net work we are getting, and that is in a cyclic manner. What we can do, had this cycle not been here, I mean if we consider only the low temperature part of low temperature cycle, that means if we do not consider this high temperature cycle, I mean if the high temperature cycle is not integrated with this low temperature cycle, then we had seen from our previous classes that TH should be maintained at a limit. We cannot increase TH beyond a particular limit, and that is the critical temperature of water. And we had seen that critical temperature, even at critical temperature, pressure is very high, and we even cannot, even for the supercritical boiler or supercritical plant, the design, operation and control, these three aspects are very difficult. So, what we can see by dragging this particular cycle to the lower temperature cycle, or by integrating, I can say integrating this high temperature cycle with this low temperature cycle. High temperature cycle working fluid is different. We are going to get, we are going to achieve, or we are going to exploit a few distinctive features of mercury, so that what we can do, we can maintain TH as high as possible, as maximum as possible, so that the overall efficiency of the cycle can be increased. So, this is the concept of binary cycle. So, what is the idea? Idea is, if we use water alone as the working fluid, we cannot increase TH beyond a particular limit. If we cannot increase the limit, then we cannot increase thermal efficiency beyond a particular value, but we need to use water because it is predominantly used, and also it is having a few distinctive features, and it is because of this properties water is used. So, we are keeping the provision of using water in one part of the cycle where temperature is less, but at the same time we need to have high thermal efficiency. That is why this high temperature cycle is added. So, these two cycles are added, and as a result of this, the efficiency of the plant will increase. Question is, it is basically that we can use, because mercury, though mercury does not have all these desirable properties, but we are using. So, definitely this fluid is having a few advantageous features, that is why it is used, but we also need to keep in mind that mercury, use of mercury is not very easy. So, we shall discuss the merits and demerits of this particular fluid which is used in this high temperature cycle. Before going to conclude, if you would like to draw the TS diagram, because we also need to know the analysis part. Our entire objective to see or look at the efficiency of the plant. So, we need to have the analytical expression of the thermal efficiency, and from there we shall see that integration of this particular cycle to the steam water cycle improves the efficiency, and that we will see from that particular analytical expression. But before completing, I would like to draw the TS diagram. So, if we try to draw the TS diagram, so this is, if I draw the low temperature part, so this is and we have another you can understand the critical temperature of mercury is very high. So, this yellow color is used to represent the TS diagram of the mercury cycle. So, you know that if we give name, so this is P 1, 1, 2, 3, 4. So, this is one, 2, 3, 4, and if we give name here, that is 5, 6, 7 and this is 8. So, we can write this is 5, this is 6, this is 7, this is 8. So, what we can see from the TS diagram is that this is low temperature cycle, this is high temperature cycle. So, this is water, steam and this is mercury. What we can see that heat which is rejected during condensation of mercury in the mercury condenser, which is also known as steam generator for this particular cycle, that is low temperature cycle, that heat is gained by the water and gaining or getting this heat from the condensed mercury, water is converted into steam and that steam is used to, rather is allowed to pass through the turbine and it does work, from where we are getting work output. So, this is the overall concept of the combined and binary fluid cycle. Idea is that by using one such fluid we can use maximum temperature at which heat is added. So, this is TH. If we can increase overall efficiency, you can see that overall efficiency will be thermal will be equal to 1 minus TL by TH. So, TL we cannot have very precise control over TL, because that is fixed by the temperature at which heat is rejected to the sink, and that is basically that depends on the temperature of coolant which is available near the plant. But what we can do, we can increase TH, and to do so we have discussed about this combined fluid cycle. So, with this I stop here today and we shall continue our next topic in the next class. Thank you.